the concept of work is to try to quantify what happens when you push or pull things a certain distance. So in other words, when we think of the concept of a work, we think, well, working really hard makes us tired. So we could either work really hard by applying a force that's really big, or by taking something and moving it a really long distance. So you can kind of get the idea of the direct relationship then between force and work, or distance moved and worked. And so then when we talk about the force being constant and the distance being a determined value, then if neither of those values are changing, let's say we're always going to take 10 pounds and move it 5 feet, then we can just come up with a number 50 that quantifies the force and the distance, that combined effect, so to speak. And so for constant problems, and when we say constant, what we're really talking about is a constant force where this doesn't change. Then the value we give to the work that is done by applying that force is just a product of how big the force is and how far you're moving something. So when you talk about a practical application like a hoist is something that does kind of what the name implies, it lifts something. And so usually a hoist is this big hook that is attached to a cable, and the cable wraps itself around the drum as the drum turns. And in this case, you could have a hoist or what we would call a hydraulic lift, lifting a car from the bottom. So those are kind of the different types of hoists or lifts that maybe you've seen. And so in this case, we've got our car here. Okay, and so here's our car sitting on this platform that's sitting on the ground, and we're going to lift up that car 4 feet. And so we're going to push it from the bottom, just like you'd see at the repair shop. We're going to push it from the bottom with this big, usually it's a big circular shaft that comes out of the ground. And we're going to lift this up 4 feet. So it is now 4 feet higher than where it began. And so the distance then is going to be 4 feet. And the amount of weight is what we're lifting. So we're going to lift the 2,800 pound car by applying a 2,800 pound force. And so to find the work then that's associated with that, lifting that object that far, we're just going to, since neither of these values change, we apply the same force throughout the entire distance moved. All we have to do is multiply those two values together. So 2,800 pounds times 4 feet. And when you multiply those two values together, you get 11,200 foot-pounds. Now, this is calculus, so you might think that you could do this using calculus, and you'd be right. So looking at this from a calculus standpoint, although calculus isn't necessary, we would have to then come up with a force function to represent lifting this car. And so since the force doesn't change, that force function ends up being just a constant value, 2,800. And if we graph that, force function, then it would be, let's say it's 1,000, 2,000, 3,000. So graphing that force function might be looking something like that. And then we're going to lift it for 4 feet. So maybe, we have 1, 2, 3, 4 feet. And so this force function then looks to start to become a force function of 2,800, a distance of 4 feet. And so this 1120, this 11,200 value ends up becoming the area underneath that constant force function. And therein lies then the connection and the calculus is that if the product of the force function and the displacement ends up being the area of the shape, then we must be able to get that value for a non-constant force by integrating that force function over that incremental distance traveled. And so if we would then apply that to the constant force, what we would be saying is we would be integrating 2,800 across a force function of 2,800 across that entire distance traveled, which would be from 0 to 4. And of course, integrating that would get us 2,800x from 0 to 4, and then plugging in x would give us that value of 11,200 foot-pounds. Foot-pounds is the English unit of work. And so, so we can see that this actually is a calculus application, and we're going to use this idea of this calculus application as we get into variable forces in the next few examples. One force that is not constant but linear is the force we have to put into a spring. So if you can think of pulling on a spring, the farther you pull the spring, the harder it is to pull. And that's evident by the fact that as you pull on a spring scale, it starts out reading 0, but as you pull on it, it reads higher and higher and higher levels of force. So, and that's the result of the spring stretching. So if we look at that graphically, then we talk about this linear force function where if you apply 0 force, you have 0 stretching of the spring. And as you apply a larger and larger force, you have a more and more stretching of the spring. So we have this linear function here. And that represents the amount of force you have to pull in order to stretch the spring a certain number of inches. And again, since work is defined as the area under the curve, we could really use geometry to figure this out. So let's say we stretched a spring 1 inch, and after stretching it an inch, it read 2 pounds of force. And let's say after stretching it looks to be like 3 inches, we end up having 1, 2, 3, 4, 5, 6 pounds of force. Okay, and after 4 inches, we have 8 pounds of force. So if we notice then, we could calculate the work really anywhere along here. If we want to know the work involved in stretching it from 0 to 1 inches, so from its free length. That's what and that just basically means unstretched. To 1 inch, we would figure out the area of that rectangle. If we want to know how much work is involved in stretching it from 1 to 3 inches, so in other words, we get the spring when it's already stretched 1 inches, and we stretch it out to 3. So we're only really pulling it 2 more inches. We would find the area of this trapezoid here. If we wanted to find how much it would take to stretch it 1 last inch, or in other words, from 3 to 4. So we're not concerned with the work done up until 3, but we're only concerned with the work done from 3 to 4. We would find the area of this trapezoid here. And all of this is additive too. So if we wanted to find the total work done, we would just add the areas of those three shapes. So it can become very geometric if the shape is linear. But we can also do this using calculus, and we'll see that in the next example. And then, of course, the other scenario is that we could get into more complicated functions where we would definitely need calculus. When we would graph these on a graph, there would be no way we could use geometry to find the area. So calculus would definitely be necessary for these functions here. So in dealing with non-constant forces here, or variable forces, we get into our calculus definition here, and that is finding the incremental work done as we move or stretch something from position A to position B, stretching being mainly in regards to a spring. And I put this out a couple slides ago. Here's that expression using calculus where we need to come up with a force function, and then we need to, that force function will change depending upon where we are on the path from A to B. And so if we look at the example down here, dealing with a spring, we're going to look at that in a second. We will look at some other examples dealing with these functions as well. Hooke's law is what we're going to deal with springs. And Hooke's law basically says the force is proportionate to the amount of stretch that we have. So that's Hooke's law. Universal gravitation is that the force is a function of the inverse square of the distance. And so it looks something like this, where the m's are masses, the g is a constant, and the distance between the masses is squared, so that we call that an inverse square relationship. And these two forces, just to put a physics spin on this here, these two forces are what we call restoring forces, and so they really have minus signs in front of them if you were to see them in a physics classroom, but that's a little bit beyond the scope of the calculus discussion that we need to have. We will let the physics teacher have that. Coulomb's law then is the electrostatic force between objects, and this either attracts or repels. So when we talk about an electrostatic force, we just talk about the magnitude. So we just look at the positive. And that has to do with the charges. So we have two charges. They can either be like or different, and that will determine whether they attract or repel. And again, it's an inverse square. So it also has a distance squared in the denominator. Inverse means it's in the denominator. It's the opposite of the numerator, and square again, because it's squared. So this is also an inverse square law. And we'll get into those a little more in physics than we do in calculus, really. So let's take a look at the spring force here. This is a Hooke's law. And the first thing we need to do with the Hooke's law type problems is to find the constant K. And so we do that with this information we have here. We know we have a spring, and it requires 5 pounds to stretch it 4 inches. So that allows us then to find the value K. So we have a 5-pound force, and it's going to stretch it 4 inches. And so if we solve for K here, K is 5/4, or 1.25. So we know K is 1.25, and excuse me, I think that's only 1.2. Yeah, that's only 1.2. My mistake. 1.2. And the units on that, if this is pounds and this is inches, this is 1.2 pounds per inch. In other words, for every inch, no, there's 1.25. For every inch you stretch it, you're going to require 1.25 pounds of force. So now that we know the spring constant k, we can now get the function. The function is 1.25x. And so once we have the function, it's just a matter of integrating it. So here's the function 1.25x. If we stretch it an inch, then we've put 1.25 pounds. If we stretch it 2 inches, we put 2.4 pounds. If we stretch it 4 inches, we put 5 pounds. So here is that point that allowed us to get 1.25. And if you notice, all we're doing is going up 5 over 4. So this 1.25, this k, is really just the slope of the line from an algebraic standpoint. So, slope of the line. And so what we want to do is we want to stretch the spring. And we know the spring is 7 inches. Okay, so the 7 inches is the free length. Okay, so the 7 inches is the free length. And it says here in the problem, we want to stretch it from a length of 12 to a length of 16 inches. Okay, and that's the total length of the spring. And so you have to ask yourself, if we know the spring is typically 7 inches long, and we get the spring when it's 12 inches, then how much has it stretched if it's now 12 inches long? And so if it's 12 inches long, it has stretched. It has already been stretched 5 inches. And so this is that point on the graph. Because remember, this is not the length of the spring here, this is the stretch. It is how much it has been stretched from its free length. Okay, if it hasn't been stretched at all, then it has no force on it. If it's been stretched 4 inches, it's got 5 pounds of force on it. So we are starting here, okay, with a stretch of 5 inches. And then if we stretch it to a length of 16 inches, excuse me, if we stretch it to a length of 16 inches, then now how far is it stretched? So here it's stretched to a length of 16 inches, and if it starts out at 7, so it must be stretched 9 inches. So that represents this location on the graph. So we're really looking at finding the area of this trapezoid here. Okay, that's the work done to stretch it from 12 to 16 inches in length, which would be stretching it from a distance that is 5 inches to a distance of 9 inches in stretched length. So the work associated with it then is we're going to stretch it. We're going to get the spring when it's already stretched 5 inches, and we're going to stretch it out until it's stretched 9 inches. And we're going to stretch the spring that has a constant of 1.25. And so after we integrate this, we're going to get 1.25 times x squared over 2. Now we're going to have to evaluate that from 5 to 9. And so evaluating that, let's see, 1.25 divided by 2. Well, let's not worry about that. We'll just keep the 1.25 out there. And so we've got 81 over 2 minus 25 over 2. And if we evaluate that, that ends up being 35 inch-pounds of work to stretch that this distance on the graph. And if we looked at this graph right here, and we found the area of that trapezoid, that area would be 35 inch-pounds.